Every time you open a browser, your traffic travels through a chain of networks you do not control. Your internet service provider sees every domain you visit. Public Wi-Fi operators can watch every unencrypted packet. Governments, advertisers, and network middleboxes all sit somewhere along that path. A VPN promises to change that equation. But what is it actually doing to your data? A VPN, or virtual private network, creates an encrypted tunnel between your device and a server operated by the VPN provider. Instead of your traffic traveling directly to its destination, it first travels inside that tunnel to the VPN server, exits there, and then continues on to the website or service you requested. From the outside, all anyone can see is that your device is sending encrypted bytes to the VPN server. The real destination is hidden. The word tunnel is not just a metaphor. Technically, your original IP packets are wrapped inside a new outer packet. This outer packet is addressed to the VPN server, while the inner packet carries your real request. The process is called encapsulation, and it is the same idea used in many networking protocols. The VPN server receives the outer packet, unwraps it, and forwards the inner request to its actual destination on your behalf. Encryption is the other half of the deal. Before your traffic leaves your device, it is encrypted using a symmetric cipher, typically AES256, GCM. The VPN client and server negotiate a shared key at connection time, usually via a Diffie-Hellman exchange, similar to what TLS uses. That shared key is never transmitted directly, which means even if someone intercepts every byte of your traffic, they cannot read it without the key. Modern VPNs use one of several protocols to handle both the encapsulation and the encryption. WireGuard is the newest and fastest, using state-of-the-art cryptography with a codebase of only about 4,000 lines, making it easy to audit. OpenVPN is older and more widely supported but heavier. ICAV 2 over IPsec is common on mobile because it reconnects quickly when you switch networks. Each protocol trades off speed, compatibility, and auditability differently. When you connect to a VPN, the first thing that changes is your apparent IP address. Websites you visit see requests coming from the VPN server's IP, not yours. This is why VPNs are used to access region-locked content and to make tracking by IP address harder. It is also why your ISP can no longer see which sites you visit. All they see is a persistent encrypted connection to one IP address. But there is an important nuance about what the VPN actually protects. DNS queries are one of the most common leak points. DNS is how your device translates domain names into IP addresses. If your DNS queries leak outside the tunnel, a network observer can see every domain you visit even without seeing the traffic itself. Well-configured VPN clients route all DNS queries through the tunnel and use the VPN provider's own DNS resolver to prevent this. There is also the question of what the VPN provider itself can see. When you use a VPN, you are shifting trust. Your ISP no longer sees your traffic, but the VPN provider does. A VPN provider that logs your activity and your real IP address offers far less privacy than one that does not. This is why the logging policy, the legal jurisdiction of the provider, and independent audits matter enormously. The tunnel protects you from the network but not from the tunnel operator. A split tunnel is an optional configuration where only some of your traffic goes through the VPN. Your work applications might route through a corporate VPN while your general browsing goes directly to the internet. This reduces load on the VPN server and avoids the latency penalty for traffic that does not need protection. The trade-off is that split tunnel traffic is visible to your local network and ISP again. VPNs do add latency. Every packet makes an extra hop to the VPN server before reaching its destination, and the encryption and decryption add CPU time on both ends. A well-operated VPN server nearby might add only 10 to 30 milliseconds. A poorly located server on a congested network can add hundreds. This is why the physical distance to the VPN server and the quality of the provider's infrastructure matter for performance. The kill switch is a feature that blocks all internet traffic if the VPN connection drops. Without it, a brief VPN disconnection causes your device to fall back to its normal routing, instantly revealing your real IP and unencrypted traffic. A kill switch prevents this by using firewall rules that only permit traffic through the tunnel interface. On most modern VPN clients, this is a setting you can enable, and for serious privacy use cases it should always be on. IPv6 is another subtle leak vector. Many VPN implementations only tunnel IPv4 traffic. If your device has an IPv6 address and the VPN does not handle IPv6, websites that support IPv6 will see your real IPv6 address. Properly configured VPN clients either tunnel IPv6 as well or disable it entirely. Checking for both DNS leaks and IPv6 leaks after connecting is good practice. It is worth being clear about what a VPN does not do. It does not make you anonymous. It shifts which organization can link your traffic to your real identity, but it does not eliminate that linkage entirely. Browser fingerprinting, cookies, and logged in accounts all track you regardless of your IP address. HTTPS already encrypts the content of your traffic in transit. A VPN adds protection for the metadata, the timing, and the destination of that traffic, but it is not a replacement for good browser hygiene or end-to-end encrypted messaging apps. That is what a VPN is actually doing to your traffic. Thanks for watching.